Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and very good day. Okay, for part number 6, we will discuss about throttling valve. What is throttling valve? So throttling valve actually any kind of flow restricting devices that cause a significant pressure drop or temperature drop in the fluid. For example, adjustable valve, capillary tube, porous plug normally for the air conditioning and also refrigeration application. Okay, so we have valve, adjustable valve, porous plug, and also the capillary tube. So normally this kind of device we will use for air conditioning and also refrigeration application. Okay, now we will discuss about the characteristic of the throttling device in terms of energy transfer. Okay, so the characteristics are, first, the rate of heat transfer Q dot. So due to small size of the throttling device, there is no large area involved, so insufficient time for heat transfer process for the throttling device. So for this case, we consider that Q dot will be equal to 0. No heat transfer process involved in the throttling device. Okay, next about the rate of work, W dot. No work done for throttling device because inside the throttling process, we don't have any mechanical movement, boundary work, and so on. Okay, so we consider W dot also equal to 0. In terms of potential energy, PE, the potential energy change very small in the throttling device, so the change of potential energy can be neglected in the process of throttling device. So delta PE will be 0. Same goes to the kinetic energy. So the increase of kinetic energy is insignificant during the throttling process. So the change of kinetic energy also can be neglected during the process. So delta KE equal to 0. So if we implement all these characteristics to the energy balance equation for the steady flow process, so we will have no Q in dot and also no Q out dot, no W in dot and also no W out dot. So the term for kinetic energy can be neglected, and also the potential energy term also can be neglected in the equation. So the remaining terms are only the term for E mass in and also E mass out in terms of the enthalpy value. So the total in M dot multiplied by H equal to the total out M dot multiplied by H. For the throttling device, we only have one inlet and also one outlet. Okay, so the mass flow rate value at the inlet and also at the outlet will be the same. So we can cancel out the value of M dot in the equation. So the final equation for the throttling device will be H1 more or less equal to H2. Okay, the enthalpy at the inlet will be equal to the enthalpy at the outlet. Example 4.9, refrigerant 134A enters the capillary tube of a refrigerator as saturated liquid at 0.8 megapascal and is throttled to a pressure of 0.12 megapascal. Determine the quality of the refrigerant at the final state and the temperature drop during this process. Okay, so from the question, the substance that we use in this throttling process is refrigerant 134A, which means the data or the table that you need to refer is the table for refrigerant 134A. Okay, and the question asks you to determine what I call the quality in terms of X value at the final state, which is referred to state number 2, and also the temperature drop during this process, which is the temperature difference between what I call the temperature at the inlet and also the temperature at the outlet. Okay, first draw the schematic diagram for the capillary tube. So we have different diameter of capillary tube. So at the inlet, in terms of substance, is R134A, and the phase at the inlet of the capillary tube is saturated liquid, and the pressure given for P1, state number 1, equal to 0.8 megapascal. Okay, so the initial state now refer to state number 1, state at the inlet, and the final state refer to the state number 2, state at the outlet. Okay, for the outlet condition, P2 equal to 0.12 megapascal, and the question asks you to determine the value of X2, the quality of the refrigerant. Okay, first we determine the important properties at the inlet, where we know that the data given P1 equal to 0.8 megapascal and the phase is saturated liquid. So because the phase already given, so no need to check the phase of the refrigerant at the inlet condition. So now we need to refer to the saturated R134A table in order to obtain the value of the important value for the inlet condition or for the state number 1. Okay, based on the table of saturated refrigerant, based on pressure table, so we can determine the value of H1, where the value of H1 equal to HF at 0.8 megapascal equal to 93.42 kilojoule per kg due to the phase for the state number 1 is saturated liquid. And the temperature for state number 1, T1, will be equal to T saturated at 0.8 megapascal, which is equal to 31.33 degrees Celsius, and we can obtain the value from the table, from the same table. At the outlet, or at the state number 2, which is also referred to the final state, P2 equal to 0.12 megapascal, and we need to refer to the saturated R134A table to check the phase. However, we only have one data, which is P2, so we need to have another data in order to use the saturated R134A table to check the phase for state number 2. Okay, so we can manipulate the characteristic of the throttling process, where we know that for throttling process the enthalpy value is constant, where H2 value will be equal to H1. So now H2 equal to H1 equal to 93.42 kilojoule per kg. So now we already have two data. First we have the pressure data, and also the second one we have the enthalpy data. Okay, so by using the saturated R134A table, we need to determine the value of HF, Hg at 0.12 megapascal in order to check in order to compare the value of H2 with HF and also Hg. So if the value of H2 greater than Hg, so the phase will be superheated. If the value of H2 lower than HF, so the phase will be compressed liquid or subcooled liquid. If the value of H2 in between HF and also Hg, so the phase will be saturated mixture. Okay. Also find the value of HFG. Maybe later on we can use this data in order to obtain the value of X2. Okay, next at the outlet, after we make comparison, we observe that the value of H2 is in between HF and also Hg value, so the phase will be saturated mixture. Okay, so now H2 equal to 93.42 kilojoule per kg. Because the phase is saturated mixture, so we can take what I call T2 equal to T saturated at 0.12 megapascal through the saturated R134A table, which is equal to negative 22.36 degrees Celsius. Okay, so in order to obtain the value of X, so we can manipulate what I call the enthalpy equation for saturated mixture region, where we know that the formula for enthalpy, H equal to HF plus X multiplied by HFG. So for this case, H2 equal to HF at 0.12 megapascal plus X2 multiplied by HFG at 0.12 megapascal. So rearrange the equation, so we will get the value of X2, where X2 equal to 0.34, which is also equal to 34%. 34% in vapor phase, the rest will be in liquid phase. Okay, so in terms of what I call temperature drop, so we already have the value of T2 and also T1. We just subtract T2 minus T1. So the temperature drop during the throttling process will be negative 53.63 degrees Celsius.